It's okay?
Okay, okay. Now it's clear.
But did you see the previous slides? Hung, did you see the previous slides?
Yes, but smaller.
Okay, it's fine. Yeah.
Okay, it's okay. Okay, so non-uniform ellipticity means that this ratio goes to plus infinity when the size of the gradient variable goes to plus infinity. So there is a competition because you want to prove that the gradient is bounded, but essentially the quantity that controls ellipticity blows up essentially when the gradient becomes unbounded. So there's a competition. And we will see that if this ratio goes to plus infinity too fast with respect to the Z norm, then you may lose some regularity. Okay, non-uniform ellipticity is a classical topic, and there are very many papers. For instance, originally it was considered in the setting of minimal surfaces because the minimal surface operator is a non-uniform elliptic operator. And then there are classical papers, for instance, by Ladyzhenskaya Ural'tseva, by Neil Trudinger. This is another classical paper of Neil. These are the golden times of this elliptic regularity. And then there's another classical one by Leon Simon. This is just to give 3 prehistoric examples of non-uniformly elliptic regularity papers. Okay, so there's a straightforward connection with functionals with no standard growth conditions. Essentially, these are functionals that are coercive in a space that is W1P, which is strictly larger than the one where they are bounded. So it's W1Q. So that there is this ambiguity. Typically, such functionals exhibit some features of non-uniform ellipticity. So examples of these functionals are, for instance, these slight perturbations of functionals with P growth, or functionals with almost linear growth conditions. So this is still functional that it's super linear, but it's almost linear. So then there are functionals, let's say energies, that are continuously oscillating between these 2 different exponents. This oscillates obviously with a logarithmic sign fashion between 5 and 3. Because when you see sine goes to 1, and then it's 5, and then it's -1, it's 3. And so you have, when du goes to plus infinity, this continuously oscillates between 2 exponents. Yet another structure is this one of anisotropic growth conditions. And this was first pioneered by Marcellini in a paper by 87, but I'm coming to this later. And you see here, you're penalizing every partial derivative with its own different exponents. So globally, you cannot bound the energy with the same exponent from below and from above. And then there are wild examples. Wild examples like when you combine several exponentials. So it is one of the paradoxes of this theory that this functional that should be hyper-regularizing with respect to the gradient boundness, because you see, when you penalize the energy, then it tends to keep the gradient lower and lower because, I mean, of the fast growth condition. Imagine that you get infinitely many exponential, you go to L infinity norm, and then it's, so it should be easier to prove regularity, while it's actually the opposite because this energy density doesn't satisfy the so-called delta 2 condition. Then we shall see how to fix this later with a different technique. Okay, so the first thing that you get is that there are classical examples by Giaguinta and Marcellini, and then positive results by Marcellini. These are pioneering results of almost 30 years ago, that tells you that if the gap ratio between the boundness and the coercivity space is too far from 1, then you may lose regularity. This corresponds, as we are going to see later, to the fact that this ratio between the highest and the lowest eigenvalue grows too fast with the gradient variable. And when it grows too fast, then you lose regularity, because in this competition, you lose. In particular, let me get a model result by Marcellini, which is by now a classical result. This is the first general results of these functionals. Actually, Marcellini was the one who pioneered in a systematic way the theory of non-uniformly elliptic operators in the setting of the calculus of variations, because in the setting of the calculus of variations, you can tell much more than in equations. Okay, then what you do is the following thing. You prescribe that the lowest eigenvalue is bounded from below by a p power of the gradient, and this is this lower left-hand side inequality. The right-hand side inequality tells the same, and then you're bounding the highest eigenvalue by q minus 2. So what are you coming up with? Is that the ratio between the highest and lowest eigenvalue grows as z to the q minus p. So if q minus p is too large, then this growth is too large, and you might end up with counterexamples to regularity. Actually, you end up with examples of unbounded minimizers. So remember that here we are discussing Lipschitz continuity. Okay, and in fact, the opposite also is true, that if you are able to bound q over p by 1 plus 2 minus n, every W1p local minimizer, so let me recall you that by the lowest growth condition, any minimizer is automatically in W1p because it makes the energy finite, and therefore by coercivity the W1p norm finite, then any local minimizer is also Lipschitz continuous. So this is the first result, the first general result in this setting, and is due to Marcellini in this by now classical paper. And this is Paolo Marcellini. Yesterday I put pictures of the many contributors to regularity. Yesterday there were pictures of Trudinger, Caffarelli, Ladyzhenskaya Ural'tseva starting from De Giorgi, and today there are these the main contributors to this theory. So actually, you can also, there's been quite a large activity in order to get better results. And let me tell some recent results, for instance, by Bella and Schaffner. There are two very interesting papers by these two authors. I never met actually them in person. For instance, in the last one, they were able to improve the previous bounds going from n to n minus 1. Essentially, what you do in order to prove this result, you apply Sobolev embedding, and then Sobolev embedding allows an iterative Moser or De Giorgi type process that improves as long as the embedding exponent is better. So what they do, you know that the embedding exponent, the Sobolev embedding exponent, decreases when n goes to plus infinity, when n increases, and therefore they are able to apply essentially Sobolev embedding on surfaces rather than on volumes. Then there's another paper by Hirsch and Schaffner that show that under the only growth of PQ conditions and under this bound, which is sharp by Marcellini's example, then the minimizer is in L infinity. And this is sharp by Marcellini's example. And then there's a very interesting recent paper by De Filippis, Christensen, and Quoc. Then they are able to get these further improved bounds under additional conditions on the conjugate function. And this is done by duality methods. This should appear, I mean, the preprint should be out very soon. Okay, you can do more. For instance, when minimizers are bounded, you can relax the bound on the gap, and you can make it independent of the dimension. For instance, this bound was first discovered by this pioneering paper of Ural'tseva and Ural'tseva. They deal with anisotropic functionals, so special growth conditions, and they were able to show that if Q is less than P plus 1, then any minimizer is Lipschitz. Any bounded minimizer is Lipschitz. So you assume that a minimizer is bounded, and then you prove that it's Lipschitz getting a better bound. So this is a result of interpolative nature, and I'll come to this later on. So for instance, the boundance of the fact that the minimizer is bounded is not very difficult to prove in certain settings, because for instance, it comes from a maximum principles, especially in the vectorial case, but also especially in the scalar case, but also in the vectorial one, and then you get a maximum modulus principle. So these are examples that how you can improve it. And then later interesting results are due to, for instance, to show. And then there's a recent paper by De Filippis and myself, by Cristiana De Filippis and myself, where this is further exploited. Okay, for instance, a recent very, very nice, interesting result by Busquet and Brasco, and they proved that when you have a special structure, so when you specify a special structure, and this is very much in the tradition of the calculus of variations, when you abandon this, let's say, abstract nonsense of general PQ growth conditions, but you specify on certain special structures, then you can say much more. For instance, the rigidity of this structure, the fact that the functional, it is self-controlled by a special structure, then you can penalize every derivative by itself. And then you can get that a bounded minimizer is actually Lipschitz continuous, provided nothing, no bound on PQ. This is a special fact of this functional, which is not elliptic in the usual sense, because it's orthotropic functions. Okay, this is a bit of the basic theory. Okay, now I'm coming to the original problem, that is, we fix F and we want to know what's the best space as F has to belong to in order to get that minimizes our Lipschitz. So let me specify the assumptions. The assumptions are pretty general in the sense that you require that, okay, you prescribe that this is the lowest eigenvalue and this is the highest eigenvalue. And then you prescribe a balance condition that tells that the ratio between the highest and the lowest eigenvalue is bounded by a power of this energy. Condition of this type was first considered many years ago by Marcellini in a scalar paper on where he proves certain results on exponential growth functions. Okay, this is the basic assumption. H is a power. I do not specify what is exactly the assumptions, because this is an introductory talk and I do not want to bother you too much, but essentially this is the power, this is the basic assumption. You prescribe that the non-ellipticity ratio or the ellipticity ratio grows not faster than a certain power of the lower density, the lower energy density. And then you can prove this result that tells that that the space, the Lorentz space Ln1 is essentially a universal space, because this tells that whenever you get a divergence type operator, then no matter what you have under the sign of divergence, if there is ellipticity enough, then the space is always the same. So if the right-hand side belongs to Ln1, so this Lorentz space, this Lorentz limiting space, then you can bound the full strength of the energy with this a priori estimate. So this a priori estimate looks a bit weird at the beginning because, okay, on the right-hand side you get what you expect. You get the energy plus data, and the data there is in the natural norm. Then on the left-hand side you have this strange quantity, but this strange quantity is exactly what you expect. Why? Because, for instance, in the case of P Laplacian operator, G1 is T to the P minus 2. So G1 S times S is S to the P minus 1. When you integrate, this is du in L infinity to the P norm. So that's exactly what you expect. This result is valid both in the scalar and in the vectorial case. So it tells you that this space is universal with respect to the Lipschitz property of minimizers. So the idea is that whenever you have an operator that guarantees regularity, and it's in divergence form, then the right-hand side, it's always that one, which is essentially provided by Sobolev embedding theorem, because you get the divergence of something is in Ln1. So trade divergence with a gradient, and you get that the gradient of something is in Ln1. But when the gradient of something, of a function, is in Ln1, then that function is continuous and in particular bounded. One thing I would like to add is that for these uniformly elliptic for these non-uniformly elliptic problems, once you prove that minimizes are Lipschitz continuous, then the rest comes for free, because then you go back to the realm of uniformly elliptic problems, because the problem is typically only at infinity, and then you can prove that it's continuous too. So once you prove this, then for reasonable functionals, then you also prove that U is continuous, and then you get a non-uniformly elliptic Stein theorem. Okay, so the new features of these proofs are, so we get a nonlinear potential theoretic approach that provides also a new proof in the standard case, f is equal to 0, and then also in this case, we get new estimates. Then the whole idea is to make a trick that reduces non-uniformly elliptic operators to uniformly elliptic ones. So therefore, with this trick, and I'm going to go back on this trick later on, with this trick in your hands, then you can reduce the theory to the uniformly elliptic one. So all the previous results are covered, essentially up to 1 year ago. And there are also new results in the classical uniformly elliptic setting. For instance, we can provide local analogs of some recent results of Chunky and Mazia. Chunky and Mazia deal with a certain boundary conditions for uniformly elliptic case, and we can do a local analog of these results. And in the case f is equal to 0, we recover the classical theory of Marcellini, of Lieberman, and so forth. And also we cover the Olid space setting. So for instance, when you apply this result and this estimate in the classical uniformly elliptic setting of the P Laplacian operator, where f of the u is equal to the u to the p, then you get the usual estimate that Tuomo Cusi and myself were able to prove for the P Laplacian system. This also goes back to a previous, this precise estimate also goes back to a previous paper I have with Frank Duzard many years ago. When you put yourself in the realm of PQ growth conditions, sorry, there's a typo, there should be a P here. Then we go back to Marcellini's estimate. So Marcellini's estimate is covered as a particular case of this general theory. Then we can cover fast growth conditions. For instance, get me any iteration of exponentials. Then if f is in the Lorentz space Ln1, then you get that the gradient is bounded. And this is a new estimate also. This is an estimate which is new also in the case when f is equal to 0. When f is equal to 0, the local Lipschitz continuity of minimizers of this function was proved by Marcellini. But here we are able to recover this result with a sharp estimate. So we are able to prove that you have a local bound of the gradient. I must have done something very bad here, but I don't know what. Or maybe someone else. Okay, you can bound the gradient by the log of the mean average of the exp. So that log and exp, in a certain sense, they cancel dimensionally, and then you get the usual estimate. The estimate you expect. The previous estimate by Marcellini's paper, features a loss of an exponential rate. Essentially, we are able to get the sharp estimates because of the new technique that allows to reduce non-uniformly elliptic problems to uniformly elliptic ones. So there's essentially no difference with this potential theoretic approach. For instance, we are able to prove this estimate was for a long time an open problem. So the idea is the following one. You get a functional which is defined in Lorentz spaces, in Olid spaces. So you minimize, let's say, A of the modulus of the gradient, where this is an Olid function. And then we are able to get this estimate, which was an open problem for a while. And that's exactly the generalization of the previous estimate. You can bound the gradient by A minus 1 of the mean average of A of the U. And this was known only under the additional assumptions of the delta 2 condition. So if you have delta 2 condition, then you can get this. And these are classical results by Talenti, by Cianchi-Fusco, by other people, by Lieberman, and by many people, but only under the delta 2 condition. Here we are able finally to remove this delta 2 condition. Okay. Okay, what I've done up to now is the following thing. Look at this example. For instance, I analyzed the influence of the data F. So the data is an external ingredient on the analysis. I mean, I analyzed the impact of the external ingredient on the regularity of minimizers. So there's, so when the external ingredient is on the right-hand side, you are in the realm of so-called Calderon-Zygmund theory. But then there's another way to put the external ingredient, and this is when you get coefficients. When you get coefficients, you go to the realm of another theory, which is Schauder theory. So this is perturbation theory. So one thing I forgot to tell you that there is no general Calderon-Zygmund theory for non-uniformly elliptic problems, because probably there cannot be. And now I'm going to show you that there's no general Schauder theory for non-uniformly elliptic problems. In fact, we shall see interesting phenomena when we are going to see these functionals. So in particular, we are going to see that the dependence on X cannot be treated as a perturbation anymore. So usually, when you have, for instance, a dv squared times a coefficient, then you get perturbation on the coefficient. Here, perturbation cannot work. So let me go back and let me recall a few results that are by now classical in the standard uniformly elliptic setting. So you get a non-autonomous functional of this type, and then now you prescribe standard growth conditions. So it's P, P. So in particular, an example is given by a coefficient affecting dv to the P. Okay, and now you get me what is the kind of regularity you require on a minimizer, and then I can tell you what is the kind of regularity that you have to put on the coefficient. So it's very sensitive to this. So the first step is the so-called Diogenes-Moser theory. So if Cx is measurable, then the minimizer is Hilder continuous with a microscopic exponent. The exponent only depends on the ratio between the lowest and the highest value of Cx. Cx must be, of course, far from zero. It's positive and it's bounded away from zero and infinity. So this is the only result of this series which is not given by perturbation. This was the real breakthrough of the Georgi and Nash, before whom all the results of this kind were obtained by perturbation methods. Here, perturbation methods are not relevant in the first line. Then if you prescribe that Cx is continuous, then you have an upgrade from some gamma to every gamma before 1. And then finally, when Cx is Hilder, then the gradient is Hilder. And if P is equal to 2, then the two exponents coincide. For P equals to 2, this is Schauder theory. Otherwise, it's nonlinear Schauder theory. And these are essentially contributions of Giaquinta, Giusti, and Manfredi. These are classical results at the beginning of the 80s. So this is Mariano Giaquinta. This is Enrico Giusti. And this is Juan Manfredi. So these are the three guys, Giaquinta, Giusti, and Manfredi in the 80s. Okay, what I would like to tell is that in the non-autonomous case, this game of making perturbation, let's say using Korn's trick, using Schauder perturbation or whatever, so it doesn't work anymore. It doesn't work, and this makes, I mean, the whole theory more interesting, but also more difficult. Okay, you can immediately understand why it doesn't work by analyzing these three functionals originally considered by Zhikoy in the 80s. Actually, okay, the real, Zhikoy functionals are the last two. The first one is a very classical one when you get a weight next to the gradient. So you immediately have the intuition, that perturbation methods cannot work as such. Why? Okay, in the first case, W, the weight W can approach 0. So when on those points, at those points where W, if you look at the energy density, at those points where W is larger than 0, then you have the usual, Laplacian ellipticity. When it goes to 0, then you lose everything. And this is a classically degenerate elliptic problem. Second case, assume that P has two different values. So on certain points it values 2, in other points it values 3. Then the rate of ellipticity is changing according to the point. So you move the point and the rate of growth and the rate of ellipticity completely changes. This tells you that you cannot at least naively apply perturbation methods, because perturbation is the idea is that you move a bit around the point and the functional doesn't change a lot. Here you move a bit around the point and the rate of ellipticity, that's the main information at your disposal to prove regularity, then the rate of ellipticity completely changes. If Px is continuous, it changes continuously. And the hardest functional is by far the last one, which is the double phase functional, that tells you the following. You have two fixed exponents modulated by a coefficient that can be 0. So at those points where a of x is larger than 0, strictly larger than 0, you have a q growth functional. At those points where a of x is 0, you have a p growth functional. So in some sense, this is a mixture of the two. Why is it a mixture of the two? Because it behaves as a weight in the first sense, but it also behaves as an exponent variable in the second case. So in this sense, the transition is faster in this case. And let's see. Okay, this is the kind of regularity I told you before. So, for instance, as soon as Cx is Hilder in the classical case, then the gradient is Hilder. Now, what would you like to do in order to apply perturbation methods to, for instance, the last case functional, the double phase functional? So the idea is the following one. If you want to go through the standard Schauder theory, you say, okay, I get just a constant here, and it's not very difficult to prove, at least in this special case, that minimizers of this functional are C1 beta regular. So the gradient is Hilder continuous. So whenever you fix A0, and A0 is a constant, so minimizers enjoy that kind of regularity. And so, if standard perturbation methods would work, they would imply that using this as a reference result, then you're able to make some small perturbation around A of x or around A0, and then you should be able to prove that the gradient is Hilder continuous. So is this true or not? Actually, it isn't, because there is this very old example by Esposito, Leonetti, and myself that tells you the following. So get me a coefficient. So I can provide you a coefficient which is Hilder continuous with the exponent you want. Okay? So get me also epsilon. And then I can find p less than n and q larger than n plus alpha, such that a minimizer of this functional, which is by definition in W1P, is not even in W1Q. So you are not able to realize the higher integrability, basic bootstrap, eventually leading you to higher regularity. So this tells you that there start being an interplay between the rate of Hilder continuity and the distance between P and Q, showing you that if the distance between P and Q that corresponds to the, non-uniform ellipticity that measures globally a bold and non-uniform ellipticity, if the distance between Q and P is too far, and actually if the distance is larger than alpha, then you lose any kind of regularity. So you lose any kind of regularity because you're not even able to prove that the gradient is W1Q. So remember, you would like to do perturbation in order to prove that the gradient is Hilbert continuous. Say here, you're not even able to prove that it's in W is in LQ. So you lose the basic, all the basic regularity is lost under such conditions. And when things go bad, they can really go very bad. So you can make it more wild. And then there's another example by Fonseca, Mali, and myself many years ago that tells you the following. Get me an exponent which is as regular as you like. 3 times differentiable, 4 times differentiable, 1,000 times differentiable. Then you can find a coefficient, a very bad one actually, who has that class of regularity, but that nevertheless produces a minimizer that is not only in W1Q, but has essential discontinuity points that are concentrating on a singular set whose dimension is arbitrarily close to n minus p. Now, if you recall that the maximal Hausdorff dimension of the singular set of any W1P Sobolev function cannot exceed n minus p, this tells you that a minimizer of a convex scalar functional with the Lipschitz boundary data can be as bad as any other competitor. Because essentially the size of the singular set is as large as that of any other W1P function. So you get a scalar functional with the Lipschitz data, boundary data, with a coefficient which is as smooth as you like, and nevertheless, a minimizer is as bad as any other competitor. So there's a complete loss of regularity. And actually, this is this singular set is a fractal, is a counter-type set. So you produce a counter-type singularity set, singular set, when dealing with a scalar functional, which is convex and has smooth coefficients. This is very wild. Okay, so this is on the side of the negative results. And once again, the distance between Q and P must be larger than alpha. On the positive one, there has been a stream of papers, and on this specific functional, probably the most complete one is the following one that tells that if you contradict the previous bound, that is, if you assume that Q over P is less than 1 plus alpha over n, then you can prove that the gradient is Hilbert continuous. And this essentially contradicts the first. This essentially is sharp by the previous counterexample. Moreover, if you assume that you're dealing with a bounded minimizer, and this boundedness information, for instance, might come from a bounded boundary value, then you can relax the previous bound, assuming that Q is less than or equal than P plus alpha. And this is once again sharp by the previous counterexample, because in the previous counterexample, you get a Lipschitz boundary data. You get Lipschitz boundary data. So by maximum principle, you get a bounded minimizer. And that tells you that you have singular minimizer provided Q is strictly larger than P plus alpha. And then you can pretend even more. You can assume that U is C0 gamma, and then you can further relax the bound. This is a result of interpolative nature. The more you start and the less you require on the bound, on the bound. Observe that what is your ultimate point here? Your first ultimate goal is to prove that the gradient is bounded. Proving that the gradient is bounded, when you prove that the gradient is bounded, then it is very easy to deal with this functional because it essentially becomes a standard growth functional. Not exactly this, but almost there. You're almost there. Okay, proving that the gradient is bounded means that gamma is equal to 1, but if you formally substitute gamma is equal to 1 here, then you get no bound at all, as it should be. You start from the point where you want to come to, so there's no assumption. And in fact, once the gradient is bounded, you can conclude that the gradient is Hilbert continuous by a slight modification of the standard perturbation theory of Manfredi and Giaguin introduced. Okay, more. There has been a sudden interest, general interest on these double phase functionals as well. So the first results were obtained by Maria Colombo and myself in a series of papers. Then there are very, very interesting papers by Marcellini, Masco, and co-authors on this general structure. So you're not assuming that you have a special structure like the double phase type, but instead you replace the condition on the coefficient with a Sobolev condition, and then you can get similar results. Then there's a very interesting extension to these kinds of functionals that are closer in spirit to what we did, and this is by Hester and Ock. Then there's a recent very nice paper, I like it very much, by Balchi, Diening, and Surnachov. Well, the paper has a bunch of very interesting things developing by some old constructions of Zhikoy, who was a real genius, and also these three guys, they did a very nice job here. But the thing I like the most on my side, of course, is that this paper allows me to tell that my previous result was sharp. Because then in this paper, working from this paper, then you can prove that all these three results are sharp. So the first two results were sharp by the counterexamples we gave with Esposito Leonetti and Fonseca Mali. Then also the third result that I got with Baioni and Colombo is sharp by this recent construction by Balchi, Diening, and Surnachov. Then there's an extension given by the Filippis Min on OH. There's another very interesting, the Filippis and Palatucci. That's the first regularity results in the case of fractional operators. Why aren't we fractionalizing these operators too? Why not? And this is the fractional version of the first results. Then there's another very interesting paper by Cristiano De Filippis dealing with fully nonlinear operators with double phase type degeneracy. Recent results by generalized minima are by OK and are related to Hester and Mi-Kyung Lee. And then there's a final series of very interesting papers by Byung and his students dealing with higher integrability of the gradients and Calder-Zygmunt theory. I'm not expanding too much on this case because as far as I could understand, he's going to tell something about that. But so for this, I strongly recommend to follow the tomorrow's talk, I guess. Okay. Let me give finally some explanation on the emergence of this bound. So why there is this sharp interaction between the rate of Hilbert continuity and the gap Q over P? Because essentially the rate of Hilbert continuity allows to calibrate the balance between the potential blow up of the ellipticity ratio and the fact that it stays bounded. So let me take a ball where A of x is 0. So since A of x is Hilbert continuous, is C0 alpha, then more or less it's like R to the alpha. But if it's like R to the alpha, then if I take the sup of the highest eigenvalue on the inf of the lowest eigenvalue, then I get a quantity of this type. And then you clearly see a competition here because the distance between Q minus P tends to make things bad when the gradient is potentially blowing up, while R to the alpha tends to correct it. And this is very much suggested by the shape of the counterexample, where the A of x tends to keep the energy low, although the gradient is going to be very, very far. So you see that if you prescribe that there is a balance between the Q minus P that tends to make things bad and R to the alpha that tends to make things good when R is shrinking, because regularity is just a game of how functions oscillate small when you shrink poles, and then you see where the bound is intuitively coming from. So there's a balance between the distance between Q and P and alpha. But that's an even better way to understand all this. That's even a better way, and this is a capacitory way. So I take a ball centered at the origin of radius r. So this problem generates two different kinds of capacity. So I take the coefficient, which is just a of x equal to x to the alpha. And I work on a ball centered at 0. So we have two capacities. The first capacity is generated by the first part of the energy, and the second one by the second part. So a computation tells that this is usually, as usual, r to the n minus. That the functional is generating two different capacities. And you know that regularity is there is regularity when capacities control control the emergence of singular sets. Is controlled by the other one. Therefore, you pretend this, and then you come up with a bound. So if the two capacities, they control the same sets, then that's okay. So there's another paragraph on these weighted capacities that were originally introduced by Vladimir Mazia. And there's a recent paper by Ivona Klebichka and Cristiana De Filippis on analisi matematica pure applicata. And then in this very nice paper by Klebichka and De Filippis, there is an extensive studies of these kinds of general capacities and how they can be used to control removability of sets for solutions to this non-uniform elliptic problem. So I strongly recommend this paper by Klebichka and De Filippis. Okay, underlying all these problems, there's the occurrence of the so-called Lavrentiev phenomenon. So the original constructions of Zhikoy inspired all these constructions that we have, including those of our counterexamples. And these constructions are underlying of the basic occurrence of the so-called Lavrentiev phenomenon. This is an interesting phenomenon and classical one in the calculus of variation. So you get functions, this one is dancing to the other, but yet if you get the minimum over the larger set, which is nevertheless dense in the other one, then you get a lower minimum. And this is obviously an instruction to regularity, because if Lavrentiev phenomenon occurs, then there's no regularity of minima whatsoever. So in a sense, all these conditions, they should simultaneously control the absence of Lavrentiev phenomenon and the regularity of solutions. In fact, I would like to tell you something about a recent paper with Cristiana De Filippis that tells exactly the following thing. So get me a PQ functional, which is non-autonomous, and such that the rate of Hilbert continuity is alpha. This is the way I prescribe it. So you take the equation, the Euler-Lagrange equation, which is given by this operator, and then this is Hilbert continuous with rate alpha. Okay, this is the case of the double phase energy, but now I'm considering any type of energy. So any type of energy. So I consider a functional, an unautonomous PQ functional with this type of regularity. Any local minimizer is in W1P, and then I wonder whether or not it also belongs to W1Q. And then I have this this general result of Cristiana De Filippis and myself that tells you that if you get me a local minimizer under essentially the same bound that was seen to be, to play a crucial role in the double phase case, under essentially the same bound, and the fact that there is no Lavrentiev phenomenon because we are saying that there is no general structure, well, you can tell that the gradient is in W1Q and is actually in every space LP tilde before P plus alpha. So the proof uses a bit of interpolation inequality in fractional sample spaces, delicate approximation and penalization methods, but essentially this tells that there's another, universal phenomenon, and this is okay. Okay, finally, I would like to give a bonus proof, which is a bit funny and a bit surprising. And this proof, it's, let's say, a cheap trick. Okay, before I told you that in the paper of in the paper I wrote with Lisa Beck, we found a way to treat non-uniformly elliptic problems as they were uniformly elliptic. And now let me streamline this particular case in one, special model case with non-autonomous functionals now and no data. Okay, this is a result which is already known. The result tells you that I have a functional with PQ growth. So the same PQ are on first derivatives, and I have Lipschitz continuity with respect to the coefficients. Under this assumption, since you browse through the literature, you can find long proofs telling you that if this is the bound, and this bound is optimal, this bound is optimal now, and that there is no Lavrentiev phenomenon, then you can prove that the gradient is locally bounded. So this is known. This is known by very different methods, by long proofs. Now I want to show you how this can be proven in half a page by assuming that you know how to deal with the case p equals to q. So in other words, I want to show you how to reduce the non-uniformly elliptic theory to the uniformly elliptic one in half a page. Okay. So I go back to the standard theory, and the standard theory tells me that Moses iteration implies this precise estimate. So everything here you have to pay attention to is that you have to go through the proofs and you have to derive the optimal dependence on the constants. And in particular, this is L. This is the constant L. So now I take P equals to Q such that this is L. And of course, by ring normalization, I can assume that nu is equal to 1. So therefore, I take nu is equal to 1, P is equal to Q, and then I get this estimate. So where is this estimate coming from? It's coming from the standard theory. This is coming from the standard theory. So I go through the standard proofs and I find that this is the estimate I can get. And let me tell you once again, the main point here is not really in the shape of the estimate, but in the precise dependence on the constant. Okay, so this is as long as P is equal to Q, and therefore as long as I'm dealing with uniformly elliptic problems. Okay, now I go back to the case P different than Q. In the case P different than Q, I take a ball, and of course I can trivially bound this. Z is the gradient, and I can plug out trivially the L infinity norm of the gradient by making the problem uniformly elliptic again. So what I'm doing is I'm taking the highest eigenvalue, I can plug out the L infinity norm of the gradient, and I can transform the PQ growth assumption in the PP assumption with a constant that now depends on the solution itself. So L can be replaced by this quantity. And in this case, now I can apply the uniformly elliptic estimate that now tells me this. So I didn't do anything but applying the uniformly elliptic estimate, making this trivial observation. But now I observe that I have the L infinity norm of the gradient here, the L infinity norm of the gradient here, with a different exponent. I now prescribe that this exponent is less than 1, so it can be absorbed. And this is exactly happens when the bound, the optimal bound, works. So I can apply Young's inequality. I now apply Young's inequality, And this holds for any couple of concentric balls, beta 1, beta 2. So I did nothing, just applying the uniformly elliptic theory. And now I can recall a classical but a so-called simple but fundamental lemma of Giusti, telling me that if I have this situation, I can reabsorb this by iteration. I can now apply this. And I'm done. So this is an alpha-page derivation of the previous result with PQ by making the problem uniformly elliptic. And the main trick is essentially I plug out this quantity by making a PQ growth condition, a PP1. Then I make it a PP1. I apply the estimate for P standard functional, and I get this. But after I get this, I prescribe the bound, and I can use Young's inequality. So that's where the bound sharply comes into the play. And then I do iteration. So this was the bonus, and this was the end of this talk. Thanks a lot.
Hello. Thank you very much for your nice talk. There any question for speaker? Any question and comment for speaker?
Hello, Rosario. I'm O. I have one question.
Yeah. Okay, you can ask.
Okay. For PQ growth functional, you consider only Lipschitz regularity. Then how about C alpha regularity for some alpha or for any alpha? Can you expect any upper bound for Q over P?
I think that for the double phase, there's no difference because the counterexamples tells you that the gradient, that minimizers are discontinuous. So there is no difference if you look for C0 alpha.
Okay, thank you.
Any more question?
More?
Any more question?
No questions, but I found an interesting talk by Rosario, by Giuseppe Mingione, a very interesting talk.
Thanks a lot, Paolo.